Hello, welcome to another problem session. So this is yet another really good problem from this website here. I maintain this website, so if you want to go check it out. Okay, so this is a problem where there are two people and there is a flat surface which is frictionless. They're ice skating, so it's actually it just says smooth surface, but it you can assume it's a frictionless also. So this is frictionless. Okay, so this surface is frictionless. So which means horizontal force on either of them is zero. Okay, that's what it means. Let's see, this Alan's mass is m1 and Betsy's mass is m2. So what they're saying is that the force between them, of course, when you're pushing, this will change with time, but on average, it has a magnitude 30 newtons. So if you look at just Betsy, then she has a horizontal force of 30 Newton that way on Betsy. And if you look at just Alan, then you have a 30 Newton force on Alan. That's what it means. This is a very confusing, when people say pushing on each other and then force in between. Force in between is a language people use, but for forces, whenever you come across force, think about force on an object, one of the two pairs, right? So there are two objects here, two people here. So force on this person or force on that person. When you think of like that, you'll be less confused. Okay. And this force has acted for 1.5 seconds. So for 1.5 seconds. And this is for 1.5 seconds. Okay. And the force is a direction, so we should always think it as a direction. And the question is, find the speed so to scatter 1.5 second. It's like at the end of this force, they're not touching anymore. At that point, you might say that. Let me put they're not touching anymore. So they're separated and they're moving away from each other. At t greater than 1.5 second, no longer pushing, right? So initially at t equal to 0, v is 0. For this and this person also, t equal to 0, v equal to 0. So that's the situation. And we need to find v at t equals 1.5 seconds. And actually anything after that is the same because there's no more horizontal force to affect horizontal motion. All right, so for any object, the principle is that principle we're going to use is change in momentum vector is equal to average impulse vector times delta t. This is impulse. And not delta t. Impulse already include the delta t in. So, and this impulse is actually F average times delta t. If I'm using average force, so when I integrate ft dt, over say 0 to delta t, and if this is average, then if this is average, then it doesn't depend on time and can come outside like that, and so we have f average delta t. So that's how the impulse, when you use average, it just factors out like that. So that equal to that. So what we got principle going here, that means for us delta p vector equals to f average times delta t. So we can use this, and this is a vector equation. Although this is just one-dimensional case, but always when there's vector equation, you should think in terms of vectors. And you can pick a positive direction and a negative direction if there's just one line. And I'm gonna pick this direction to be positive x-axis. Okay, I'm gonna pick that arbitrarily, that to be a positive x-axis. So anything on the other side will be negative. And when looking at that, everything that we're going to analyze here is going to be x component, f average x delta t. So I'm not going to worry about the y direction. Y direction is weight is balanced by the normal, and there's nothing interesting going on there. So on the left side, what it is. So if I look at Betsy, so on the left side, look at Betsy. So it's the mass of the Betsy, m2, and v of 2, let's call it 2, and that's going to be x, and it's the change in that. That's what this means. This is the definition, and this is change in that, and that should be average force on her, x component, times for how long this acted. So that's the equation for Betsy. So if you look at this, this is over instant. T is delta t is 1.5 seconds, and so this is actually involving from t equal to 0 to t equals to 1.5 seconds. So this is the final time, and this is the initial time. So this is the difference between those two. So m2 v2x, this at time t equals to 1.5 second, minus the same quantities v2x at time t equal to 0, and this f average t, f average x delta t. And when we work this out, this is t equal to 0, this is 0 at t equal to 0, so that goes to 0, and this is what we want, and m2 is given. So v2x at t equals to 1.5 seconds, that turns out to be this thing, f average x delta t over m2, and we can just now plug a number with the x here. The force on her is in that direction, so that's the direction of positive x-axis, so that's positive. That's a plus 30 Newton. Time is 1.5 seconds, and her weight is 50, her mass is 50 kilograms. So you can see this is 45 over 50, so 0.9 meter per second. And because this x direction is gives you x component, and it's in her direction is motion is the positive x direction, and this gives me speed is vx for her, and that's positive meter per second. So that's got A. So this is one of them for Betsy, and we can do very similar thing for Alan. However, because the force is only between them, and this force is not an external force. So for Alan, we have a choice here. Alan, I can repeat the calculation, or we can say this 30 Newton force is internal to Allen-Betsy combined system. Which means their combined momentum is not changing. So we can use that principle. So that principle will be their change in momentum of Allen x component, magnitude of this will be change in momentum of change. Let's look like this. Let me get another new slide. Okay, so this is important point. So we have Alan and Betsy. So now we look at them as one system. So this is another way of doing it. Okay, the same problem. Once we get the Betsy is going. So let's call this M2 and this is M1, and the force is only internal. And we figured out she is going this way about 0.9 meter per second at t equal to 1.5 second. And we want to know what's this guy's v at t equal to 1.5 seconds. And v equal to 0 at t equal to 0, and v equal to 0 at t equal to 0, right? Okay, so here we can say the total momentum does not change, is equal to 0. Total is 0. Okay, so what's the total made up of? It's made up of let's look at this x component. So delta px of 1 p1x plus delta p2x equals 0. And what is the delta made of? P of 1x at t equals to 1.5 second minus p of 1x at t equal to 0, and then this guy is similarly p2 of x at t equals to 1.5 second minus p2 of x at t equal to 0, and this whole thing is 0, right? Now from the given, this is 0, this is 0, and this one we figured out. This one is 50 kilogram times 0.9 meter per second. So that's the momentum for her. So his momentum will be p1x will be negative of whatever this is. I'm going to send this on the other side. So this will be 50 times 0.9 kilogram meter over second, and it's going to minus 45 kilogram meter over second. And then know the mass, then v1x, its x component speed, velocity, x component velocity will be minus 45 over 60, and this is going to be meter per second. And you can see that you have a 12 here, put out 5, 9, and then 3/4 minus 0.75 meter per second. So here's a critical minus sign here. So we were working with x in that direction. So that's why her speed is positive, her velocity is positive, I mean, and his Vx is pointed in that direction. So Vx of Alan is pointed in that direction. That means its component will be negative, and that's what this says. So Vx Alan is minus 0.75 meter per second, means he's moving to the left, and his speed is, it's going to be absolute value of Vx, because the Vy and Vz are zeros. So that's what it says, Vx, and that's 0.75 meter per second. Okay, it took a long time to do it, but we have a answer for both of them. Just to recap, we used two principles, although this one principle would be sufficient. So principles wise, we used, just to recap, one we used is for either object, just call it so either object, we said J on the object equal to change in momentum of that object, delta P of the object. I try to remember off the object, on the object. And then we said if only internal forces, then total momentum vector cannot change. So these are the two principles we used, but just using this principle twice, I could have solved the problem. But I want to illustrate that you should also be aware that there's a shortcut. Once you have applied this on one, you don't have to keep applying that principle on the second object. You can just apply on them together and use momentum conservation principle. This is called momentum conservation principle. So I'll stop here. It took longer to make this video, but I hope this is illustrative for you. So I'll see you in another video. Bye.